which is by Victor Gurarie from the University of Colorado at Boulder. We'll talk about quantum Hall network models as Floquet topological insulators. Yeah, go ahead.
Thank you for giving me a chance to speak here today, following Senthil's talk. So Senthil talked about quantum Hall effect. I will also talk about quantum Hall effect. And similar to Senthil, I'm going to pick up something which has been around since 1980s, but there'll be a different aspect of quantum Hall effect, the quantum Hall transition, which I'm going to look at from a new perspective, well, following some of the advances which happened recently in our understanding of topological insulators. So this is the work which I've done with Drew Potter and John Chalker. Let's see. Okay. So I would like first to tell you about Chalker-Coddington network model, which in 1980s, 1990s, I think, well, 1990s maybe, that was like a tool which many people used, but nowadays maybe it's used a little bit less, because it's used to describe particular aspect of quantum Hall effect, which maybe is not as actively being studied right now as it used to. So Chalker-Coddington network model, it was proposed in the 1980s to study transition and integer quantum Hall effect, but it also has this aspect, puzzling aspect, that you can look at it as a Floquet topological insulator, or as a system which evolves stroboscopically in time. Well, I'll talk about this a little bit later, but those of you who studied Floquet systems, they know what I'm talking about. The fact that Chalker-Coddington network model is really a Floquet system, it's not a conventional Hamiltonian system, was appreciated already, I would think, 20 years ago, but somehow never taken advantage of. People just talked about it as if it's kind of obvious aspect of Chalker-Coddington network model, but they didn't highlight any of the possible questions which can come up as we are trying to describe something which is time independent by something which looks like a Floquet time dependent system. But it turns out that if you look carefully at what the Floquet interpretation of Chalker-Coddington network model is, you will see that that interpretation is not a conventional topological insulator. Now, integer quantum Hall effect is the simplest example of a topological insulator, but as it turns out, Chalker-Coddington network model is not a conventional topological insulator. Instead, it's a Floquet topological insulator. And there is a lot of knowledge which we gained over the last 10 years about how Floquet topological insulators behave. And Chalker-Coddington network model fits very nicely into this framework of Floquet topological systems. And so that raises a question. It's supposed to describe integer quantum Hall effect, which is not a Floquet system, but it has all the features of Floquet systems. And that was the question which we set out to address. And so one possible answer to this kind of contradiction was that maybe Chalker-Coddington network model does not really describe quantum Hall effect. It's really a Floquet system and should be understood as such. But so that would be more speculative, because that would imply that maybe we should not be using Chalker-Coddington network model to describe quantum Hall effect, even though it's been used to describe quantum Hall effect. But now a more perhaps traditional answer, which we eventually came up with, is that actually Chalker-Coddington network model does describe quantum Hall effect and provide a bridge between Floquet systems and time-independent systems. So in fact, it has features which look like Floquet, but it also has features which look like the time-independent. And that actually shows that some Floquet systems are not as different from time-independent systems as we might have thought. And that's going to be the punchline of the talk today. Okay, so let me first tell you or remind you about what quantum Hall transition is and how it was studied for many years, especially in 1980s and 1990s. So originally, this problem was formulated in the context of transition between plateaus in integer quantum Hall effect, but it can be stated very simply on the level of a simple Schrodinger equation. So we have a Schrodinger equation of a particle moving in the magnetic field, constant magnetic field perpendicular to a two-dimensional plane, but also with a potential which varies randomly in space. And now it's known that when you have Schrodinger equations and potentials which vary randomly, wave functions which satisfy such Schrodinger equation can undergo Anderson localization. And that indeed happens. So this happens in this problem. And so the typical wave function, which is a solution of that Schrodinger equation, will be localized, which means it'll have a finite spatial extent. And the spatial extent will be controlled by the localization length, which is this L parameter here. And now, actually, if you study two-dimensional Schrodinger equations without any magnetic field, but with random potential, it's been known since early 1980s that all wave functions, all solutions of such Schrodinger equation will be localized. But here in the present magnetic field, there will be special values of the energies which will roughly correspond to position of Landau levels in the absence of random potential. So if there's no random potential, then there are just Landau levels, which all occur at some energies E0, E1, and so on. But so at these energies, though, once a random potential is turned on, localization length will diverge and go to infinity. So it will diverge around E0, around E1, and so on. So all wave functions are localized except those which live at these energies. And that's kind of important because these delocalized wave functions are the ones which are, well, part responsible for quantum Hall effect. Now, a question which was asked already in late 1980s was how fast does localization length diverge as energy approaches critical energy? Let's say E goes to E0, and there's some exponent nu, which controls how fast this thing diverges. And now it's been believed since early 1980s that this nu is approximately 2.35. I mean, it's been known from numerical simulations. Now, these numbers very close to 7/3. 7/3 in turn is 4/3 plus 1. And now 4/3 is a critical exponent for percolation. It's possible to argue that this quantum Hall effect is very similar to percolation in some way. And I will talk about this a little bit later. And so many people assume that maybe this is 4.3 plus 1, 4 divided by 3 plus 1. So with plus 1 coming from some quantum aspects of this percolation, there were papers written about it in the 1980s, but the number was very close to 7/3. And now with many simulations done in 1990s and also with experiments, you can extract this exponent from looking how, let's say, sigma xy, whole conductance changes from one plateau to another as a function of temperature. So if you vary your temperature, it starts jumping faster and faster between plateaus. And from that, you can, in principle, extract this nu. And so it's been believed that this nu is indeed very close to this number. Until in 2009, there was a strange development by Slevin and others who pointed out that actually, if you do more nicer numerical simulations, you'll get something which is more like 2.6 or maybe even 2.62. And since then, since this last decade, many of the previous numerical simulations were re-examined, and suddenly these numbers started creeping up and approaching 2.6. So people who used to say it's 2.3, now they're saying it's at least 2.5 or maybe even 2.6. Now, of course, there's also work by Zimbauer who says that actually nu is infinity, and all of this is just a result of poor numerics. I'm not clear how that well, how it jives with experimental data. But in any case, the value of this nu maybe still remains open. Nobody knows what it is. But this nu, historically, as it turns out, it was easiest to extract it from something called network model. And so network model is what I would like to explain now. So network model was invented in part so that it would be easy to calculate this nu. Instead of studying the Schrodinger equation, study something which would be simpler. So the motion of a particle which obeys the Schrodinger equation, if we could to kind of get a visualization of what it's like, we could write down a classical equation of motion, which a particle in a potential and a magnetic field obeys. And now lowest Landau level corresponds to taking mass to 0. So if we take mass to 0, we'll end up with this simpler equation, which tells us that particles move along equipotential lines of this potential. So I imagine that random potential forms some kind of complicated surface with peaks and valleys. And so if you fix the energy, the particle will move along these equipotential lines. And now if the energy is pretty high, the particle will circle around tops of these mountains. But if we lower our energies, the size of the trajectory will increase. And eventually at some critical energy, the trajectory will percolate through the whole system. In fact, this picture literally corresponds to percolation. And if this was all there is to it, if this equation was literally correct, then the percolation fiction would have been exact, and this nu would have been 4/3, the exponent with which the size of the trajectory diverges as energy is reduced towards the energy where the trajectory becomes infinite. But now, of course, in fact, this equation is only classical. The correct equation is quantum. And in fact, it's possible to correct this equation by adding non-commutativity to it, just like Sanchel was talking about. But that becomes very complicated very rapidly, and not much analytic progress, at least, was made by taking this equation and studying it making it non-commutative and understanding what that implies, what this trajectory is. But so instead, network model was invented, which, well, here is the how this network model works. So it's a set of wires, so to say. One wire propagates upwards, the other wire propagates downwards. So the propagation of the directional propagation of wires alternate. Now, a wire is just a picture or an image. What I really have in mind is amplitudes, which I call psi, which live on lengths of this picture of these wires. They sit where the arrows are. So there's psi sitting here, psi sitting here, psi sitting here, and so on. And now these psis, when they approach these red and blue islands, they scatter. And what I mean by scatter is that, for example, psi, which lives here at the length 1, and psi, which lives here at the length 2, scatter off each other with these through this red island, according to this matrix written here, which is the usual, orthogonal 2x2 matrix, and produce two amplitudes, psi3, psi4, which is outgoing amplitudes here. And so every red island is controlled by these 2x2 matrix, controlled by theta, and then blue islands are controlled by theta bar, which is pi over theta. So it's the same matrix, but with theta bar, which is pi over theta. So now this kind of like produces a picture of particles which try to circle, but if they scatter, they move away from these circles. It's similar to this quasi-classical picture, which I had before. Now, in practice, to really use it, and well, to use it for calculations, what was done back in 1980s is, so people would take amplitude sitting on these links along a particular row of links or column of links, which I call psi c. So psi c is a vector of all such amplitudes. So if you know all these amplitudes here, you can calculate amplitudes here by solving for these two amplitudes, the right side amplitudes in terms of left side amplitudes at each island. So the equation below gives us outgoing amplitudes in terms of incoming amplitudes. Instead, we'll rework it as right-hand side amplitudes in terms of left-hand side amplitudes. And so we can, if we know amplitudes everywhere along this column, we can get amplitudes all the way everywhere along this column and so on. And so we can write down these equations. The next column can be expressed in terms of the previous column in terms of this transfer matrix, which directly follows from this construction. And now it's very easy to convince yourself that if you know transfer matrix, you know localization length. And so what people were doing is they were calculating numerically this transfer matrix and extracting localization from here, and then trying to figure out how localization length changes when we change the parameter theta, which controls the angle at which we scatter. By the way, we also have this random energy, random phases added here, which creates, they mimic the disorder which we had in the Schrodinger equation. Okay, so this is all very cool, and this was successfully used to calculate that exponent nu, and actually that new result by Slavin was extracted by studying this network model, but in a larger scale simulation than people did before, and that's how nu moved from 7/3 to slightly above 2.6 nowadays. But now I would like to emphasize, though, that the way this network model works is, well, its properties depend on the value of the parameter theta. So if, for example, if theta is equal to pi over 2, and if you study exactly how that scattering happens, you'll convince yourself that particles tend to move along these great rectangles or squares. And so particles look like they're moving around top of mountains, like it was in my quasi-classical picture. And if theta is equal to 0, particles move along, around white squares. That's how scattering work out. But if theta is in between, then particles tend to kind of delocalize across the whole system. So theta being pi over 4 is the delocalization point. Okay, and now with this sense, we can reinterpret this network model as a Floquet system. In fact, it's kind of like an obvious thing to do. As I said, it was done already in the 1990s. It's just that consequences of that were not explored. So instead of thinking of this network model as a bunch of transfer processes like I had on the previous slide, where from one column here, I get this column and so on, and just extract localization length, I look at it as a full dynamic system where if I know amplitudes at a certain kind of moment in time, I apply the scattering matrices to every vertex of this model, and I generate a new set of amplitudes psi. So given amplitudes on every link, I can find out what they are at the next moment in time by taking every amplitude and making it undergo the scattering process and getting the outgoing amplitudes. So every amplitude is incoming somewhere, but also outgoing somewhere. So given a set of all amplitudes everywhere, I can generate these amplitudes at the next discrete moment in time. And so I can write down the stroboscopic evolution equation where every psi evolves according to a unitary evolution operator constructed out of these scatterings by theta and theta bar. And actually for translational independent system, if I don't have any disorder, I can write down this evolution operator in my mental space. Here it is. And so then the evolution is described by this process. So every psi evolves in time stroboscopically, meaning that by integer amounts. Now, okay, given the evolution operator, I can obviously diagonalize it. It's a unitary operator, so its eigenvalues have the form e to the minus I epsilon. And I can plot these epsilons as function of k. And so then if I do that, I'll generate 4 bands. So you can convince yourself actually that this network model has a unit cell which has 4 psis in it. So it's not surprising that there are 4 bands. So here these bands are plotted when theta is equal to pi over 4. Exactly at pi over 4, when trajectories are delocalized, bands actually touch each other. And in 2 points, they touch each other here. Well, right, in 2 points in Brillouin zone, here and here, and they touch each other pairwise. So at this point, bands 1 and 2, and 3 and 4 touch, while at this point, 1 and 4, and 2 and 3 touch. Now, if we make theta go away from pi over 4, small gaps will open, and eventually, of course, they'll become larger when theta is equal to either 0 or pi over 2. The bands become flat, and they stop touching each other altogether. Okay, so there are this interesting pattern of bands and how they touch each other if you construct this. Now, this, by the way, again, was noticed and even studied for quite a bit of time, at least for the last decade. But an interesting observation can be made now. So we know that quantum Hall effect is supposed to be described by bands which have Chern number. I mean, Chern number is a defining characteristics of integer Hall or of topological insulators in a particular class. But now we could ask ourselves, do these bands have any Chern number? Now it's very easy to convince yourself they don't. And that's in part because if theta is equal to 0 or pi over 2, the eigenstates of this problem are literally localized on these squares, either on gray squares or on red squares. And this kind of localized eigenstates cannot produce a band with non-zero Chern number. And if it's change in theta, Chern number cannot change until the bands touch. And the bands touch only once, when theta is equal to pi over 4, and they don't touch otherwise. So you know right away that these bands don't have any Chern number. The Chern number is 0 for every band. Now, we can further study what happens when theta is close to pi over 4, and it's also easy to see that each of these points the bands touch, these are really Dirac points, and that means there's a Chern density in the vicinity of these points on both of these bands which touch. One of these bands will have positive Chern density, one will have negative Chern density. But every band touches 2 other bands when theta is close to pi over 4. Well, for example, this one touches the band above, and it also touches the band all the way above here. And so here it has positive Chern density, and here it'll have negative Chern density, and these 2 Chern densities exactly cancel. So there is no Chern number for any of these bands. Okay, given that, we could ask a question, but this network model is supposed to describe quantum Hall effect. How does it do it? Furthermore, we can convince ourselves that one of the 2 phases of this network model, understood as a Floquet system, has edge states, just like topological systems are supposed to have, and quantum Hall effect is supposed to have. If we look at the situation when theta is equal to 0, so theta being 0 means everything moves along white squares. We can convince ourselves that the amplitudes which live at the very edge of the system will actually move just forward. So these amplitudes will move up and propagate along this edge because it has nowhere to scatter, no more stuff on the left from it. Well, stuff here will move along white squares. But here there are no white squares, so it'll just move along the edge. So the edge states are there, at least when theta is equal to 0. And you can argue that even theta is not 0 unless bands touch, the edge states will still be there, like always happens in topological insulators. Now the edge states have a, well, you can think of them as just being plane waves. And it's very easy to convince yourself that the eigenstates of the evolutionary period or eigenvalues of evolutionary period have the form of e to the minus ik, where k is the momentum along the edge. And that means the this kind of quasi-energies, the phase of the eigenvalues of the evolutionary period, they sweep the energy Brillouin zone. They go from minus pi to pi as k goes from, well, as k goes across the Brillouin zone. I should have actually written here maybe, well, from 0 to pi, for example, minus pi, from minus pi to pi, as k goes from minus pi to pi. Okay, so, all right. These are edge states, they're robust. And then the question comes up, how come there are edge states there if there is no Chern number? Now, this question was answered actually by Radner, Lidnerberg, and Levin in 2014. So they've shown that these kind of systems, the Floquet systems with this type of edge states, which wrap around the energy Brillouin zone, they are topologically protected, but not by Chern number, but by a new Floquet topological invariant. And the phase in which such systems can live can be called Chiral-Floquet topological phases. And they're supposed to be different from conventional whole topological phases. So let me talk about this a little bit more. So the how come that a system like this so has edge states but no Chern numbers? So the proposal by Radner and collaborators was that if a system which is a Floquet system, you know, and so that it's characterized by the eigenvalues of the evolutionary operator. And so if the quasi-energies of such system, which are phases of the eigenvalues of the evolutionary operator, if they span the whole energy Brillouin zone, they go from minus pi to pi as momentum goes over the conventional momentum Brillouin zone, such an edge state clearly is protected because you can't remove it. It sort of ties onto itself and topologically cannot be moved away from this configuration. When something like that happens, we would imagine that there is a way to tell by just looking at the bulk only and not looking at the edge that the system is topologically protected, just like we do for any topological insulator. And so these authors identified a topological invariant calculated out of the evolution operator, which if it's non-zero, it counts a number of such edge states which wind around the energy Brillouin zone. So if this topological invariant is non-zero, we say that we're now located in Chiral-Floquet topological phase, as opposed to conventional two-dimensional topological insulators, which could be topological, for example, if they have Chern number, I mean the time-independent systems. If you have dependence, you can also have...
Victor, so normally the Chern number is the coefficient of the Chern-Simons term in the bulk. So come on show that this chi number, which is also quantized, is the coefficient of some generalized Floquet, some topological field theory. So did anybody do that?
It's a very good question, and I'll be honest. I think I'm aware of some work in that direction, but I'm not aware of what came out of this. The question is actually if there is a, I mean, what even the right language to describe this kind of systems, because they are, I mean, they're not described by conventional field theories because they're time dependent. So if there is an effective sort of response term which we can use to describe this, then there's a question of what we should do to do that. And I'm aware of a work by Shinsei Ryu. I don't know if he's here today or not. And he studied this kind of question, but he would be in a better position to tell us whether I mean, first of all, if I understand it correctly that he studied that question, and second, if there's a good answer to this question, good compact answer to that question, as compact as Chern-Simons term. Okay, so, all right, but I will not talk about this aspect of these Chiral-Floquet phases. By the way, he used Keldysh formalism, as far as I understand, to study responses of the Floquet systems. Okay, so now, So this Chiral-Floquet invariant, if it's non-zero, it means that we're in a Chiral-Floquet topological phase. Now, the one interesting aspect of this invariant is that it's not enough to know the evolution operator over a single step in this stroboscopic evolution we've got here. So I'll go back. So we have this U, which defines for us how psi involves step by step. And that's the U which network model provides. But in order to construct this.
Can I ask you a quick question? So wasn't the Floquet Hamiltonian in their case simply zero? So the stroboscopic evolution could be trivial, actually. So I thought
that's true, right? Yes, you're absolutely right. So it's even possible to have trivial stroboscopic evolution and still to, be in a non-trivial phase.
But I think that's exactly what they were studying. In fact, it was actually zero because you needed the periodic evolution operator for that. Okay.
Well, you mean these authors? They studied both this and more general cases when you when.
One of the authors I think is in the panel, so maybe he is.
Well, okay. I think well, right. I know enough about this work to say that you can study this case, but you cannot study more general, even general case of some evolution operator. The subtlety here is that. We only know U here one step at a time. It's actually not one. I wouldn't call it zero, I would call it one, right? Because it's a unitary operator. It's not one, but it only tells us how things evolve stroboscopically. But now to construct this invariant and even to understand the physics of this problem, we actually need the entire evolution operator, how it depends on time, precisely because at the time equal to stroboscopic time, U could even be one. But not in our case, but it could be. And so in order to...
Can you just clarify? So we're saying invariant, what does it mean? So this number, chi of U tilde, so it's a real number, or is it quantized in some way? What is happening here?
Yes. So this number chi of U is quantized. In fact, it's a mathematical property of expressions like this. If U is a unitary matrix, which is periodic in time, and the integral is done over that period. Now, our evolution is actually...
So it should be periodic. So if U of 0 is 1, then U of capital T, whatever the period, should also be 1, right?
Mm-hmm. Yes.
Periodic evolutions. Okay.
So Rudner and Toll showed that given U of T over the period of the evolution, which might not be periodic in time, you need to complement it with an additional portion, which makes it periodic in time. And such complemented evolution operator, we'll call it U tilde, and it has to be substituted here. But there is an algorithm given U of T, which is not periodic in time, which corresponds to Hamiltonians, which are periodic in time, how to construct such U tildes to give periodic U tildes and be able to calculate chi. Now that algorithm was established and we understand how to use it, but a more non-trivial step for us would be to find out what U of T is even before we hit the stroboscopic time. In other words, so far we only know U when time is stroboscopic. But so it turns out that it's possible to supplement the network model by certain evolution rules such that they'll produce U of T for an arbitrary T, not only for the stroboscopic times. So they're based on the idea of exchange of two wave functions, so two psi's, according to this time-dependent operator. So as a function of T, that starts exchanging psi1 and psi2. If T is equal to pi over 2, that's an entire exchange, psi1 and psi2. And now we can construct a three-step process where we extract the amplitudes of the network model. But first we exchange them along these lines, then we exchange them along these lanes, and then we partially exchange them along red and blue lines with T going from 0 to either theta or theta bar. You can convince yourself that doing this kind of process generates at the end of these three steps precisely the stroboscopic evolution of the network model, which if then supplemented to produce U tilde can be used to calculate chi, and this chi will be 1. Okay, so
we have 10 minutes left.
Okay, yes. All right, so clearly then network model is a Floquet system. It belongs to these Floquet topological insulators. In fact, Floquet topological insulators were studied over the last decade quite a bit. It's been realized that conventional topological systems or conventional topological insulators, if they're driven, if they depend on time, or if they evolve in time stroboscopically, the way I showed before, they can be all classified and they produce a generalization of the conventional classification. In the simplest case, if conventional topological insulator is classified by group G, the anomalous, the Floquet topological insulators will be classified by G times G. Somehow G is the old time-independent classification, which is now supplemented by another classification having to do with H states, which can move across the entire brilliant zone, or energy brilliant zone, which Floquet systems have. Okay, and so what we've just discovered is that while integer quantum Hall effect belongs to the first G of this product, to the time-independent G, the Floquet systems, and in particular Chalker-Coddington network model, belong to the second G. Okay, and so at this stage, we are facing a puzzle. We have the network model, which is supposed to describe integer quantum Hall effect. It was designed to describe it, but it's a Floquet system really, and it's a Chiral Floquet topological insulator. So does it describe quantum Hall effect or not? One possibility was that it actually does not describe quantum Hall effect. Maybe it's in a different universality class. But it turns out this is not the right possibility. And the correct answer to this question is that network model describes both integer quantum Hall effect and the Chiral Floquet phases. And in fact, provides the bridge between these two. But if so, where is the Chern number? So to see where the Chern number comes from, we need to reinterpret what we mean by the network model, which simultaneously will give us a bridge between time-independent topological insulators and Floquet topological insulators. So when we studied network model as a Floquet system, we took theta to be an independent parameter, which was just fixed. Fixing theta at some value calculates band structure of this network model, understood as a Floquet system. But understood as a quantum Hall effect, theta is supposed to vary. If you remember this picture of percolation, theta is kind of like the energy, because when theta varies from 0 to pi over 2, it's precisely when trajectory go from circling around the peaks to going down around the valleys, and at theta being pi over 4, these are the trajectories which stretch across the whole system. So we want to make theta to be energy dependent parameter. And now exactly how to make it energy dependent? If we think about this, we can use our physical intuition. Our intuition tells us that, well, first of all, there has to be some theta energy dependence. We don't know what it is, but as energy sweeps some range across the energy brilliant zone of our network model, we would imagine that theta should go between 0 and pi over 2, hitting pi over 4 somewhere in between for the energy where we have these delocalized trajectories. Second aspect of this is that there could be also phases which are accumulated when particles move along the links of the network model. So, whenever particles move along this link, they accumulate some phase. In fact, when they go along this plaquette, they accumulate a phase, which has to do with the flux of the magnetic field across this phase, which should also be added. And so by doing so, we can convince ourselves that in order to find the energy of a particular state described by the network model, we need to solve this equation. Where epsilon n is the phase of the eigenvalue of the evolution operator labeled by n. So there are 4 of these n's, 1 to 4. There are 4 eigenvalues of u. Theta of phi is some phenomenological theta depending on e, which sweeps from 0 to pi over 2. Phi of phi is some function of phi which controls the amount of phases which accumulates when you move along these plaquettes, which in the simplest case, you just take them to be linear. If you plug this in here, you can solve for every momentum. You can solve for E and find E, which are functions of n, band number, and m, because there is an ambiguity of 2 pi m here when you match this with energies. And so you get E and m as a function of k. And these are sort of new bands. As you vary your k across momentum brilliant zone, E will vary in some way, and simultaneously theta will also vary, unlike in the previous Floquet picture, where theta didn't vary. And so a little bit of work working with this equation tells us actually that as soon as we do that, one of the bands will acquire a non-zero Chern number. So this is a result of a particular numerical study of this theta energy dependence. So these are the energy, they're shown along some, going from gamma, ym, and x points in the brilliant zone shown here. And so in particular, this band shown around here will actually have Chern number equal to 1, in part because it will approach points where bands at theta pi equal to pi over 4 touch each other. They touch at points x and y. So the bands which don't have Chern number have opposite Chern number density. This color is a Chern number density at these points. So this band, for example, does not have a Chern number, and it has opposite Chern number densities at these points, while this band below actually has the same Chern number density. And you can gain some intuition by thinking about how energy varies across these bands and how theta varies. So theta smartly varies in such a way that if you're along close to this point, theta is larger than pi over 2. And if you actually along this point is larger, and here it's smaller in such a way that Chern density will change as theta crosses pi over 4 to always give you the same sign at all 4 of these points. So a network model actually does have a hidden Chern number, and it describes both Floquet system and time-independent system. Now, I know that I'm running out of time, so once we have this picture, we can think of generalizations, and that would be essentially my last meaningful slide. One generalization would be to think about other topological insulators, and that's possible to do. It's actually fairly easy. You can take conventional topological insulators, reinterpret them as network models, and then reinterpret those network models as Floquet topological insulators, which will be in the Floquet phases, controlled by the other G, not by the first G, which describes conventional topological insulators. And you can also think of interaction system. That's especially interesting to me because originally I was motivated to think about this by thinking of the kind of models which Ashwin and his collaborators, Drew Potter and others, studied. So this model is taken from this paper here. It's now a model of interacting spins, which move according to some Floquet evolution. So they get just some spin exchange operator applied to these models along red, blue, orange, and green lines. And so the result is something which resembles very closely a network model, but it's actually a many-body interaction network model, because now we have a bunch of spins instead of just amplitudes of the wave function. And the question which I still have is whether this has anything to do with time-independent systems in the way how conventional topological insulators, as it turns out, can be thought of as Floquet systems. So I don't have the answer to that question, but let me just summarize what I told you by listing the following results. So first of all, Chalker-Coddington network model describes both chiral Floquet topological insulators and Chern insulator. It provides a map between the two. It actually shows that quantum Hall transitions for integer Hall and for chiral Floquet insulators, they lie in the same universality class. This, by the way, was already noticed by people who studied transitions in chiral Floquet systems. They observed that transition should be in the integer Hall universality class, and this gives an umbrella picture of why this is so. And in fact applies not just to quantum Hall, but also to all topological insulators and transitions in those, as well as transitions in chiral system, transitions in driven Floquet systems. And I guess the last question is interactions. And we think that possibly for interactions, similar construction will work in 1D, but maybe not in 2D, in part because classification of 2D interacting topological insulators is so much different from non-interacting systems. But I would say, in my opinion, this question is still open. So what happens for interacting systems? Okay, so let me finish here.
Yeah, thanks a lot, Victor. So we have a few questions. So the first is from Ilya Grusberg. Actually, I just put him on the panel, so maybe he can ask you his question directly.
Hi, thanks, Ashwin. Hi, Victor. Quick question. So this Floquet, chiral Floquet invariant that you wrote is similar to TKNN. So it's an integral of a Brillouin zone, right? But in a disordered system, you would need another kind of invariant to, quantify, to quantize anything, right? So it's like a tau-less Neo invariant with a flux threaded through the torus, right? So is there an invariant of that type for chiral Floquet system, but in a disordered situation?
Mm-hmm. Yes, so I didn't study it, but I would imagine that it's relatively simple to replace this momenta by fluxes threaded through the system in the same way how we do it for conventional topological insulators. and still get topological invariant, but now in terms of these fluxes. So I don't see any obstacle to doing this. There could be more sophisticated approaches, kind of like Matt Hastings was studying.
Yeah, yeah.
But
Yeah,
in a simple-minded case, that's what I would do, and I think it'll still work.
all right, thanks.
So we have another question from Dominic Els. Again, he's maybe he can ask you directly the question. Dominic?
Hello. I was speaking. Yes, I wanted to ask, it sounds like in those template picture you described the Floquet model, the non-spatial relation band. But then it seems like what was suggesting, or maybe I was interpreted, they are often associated with topological Floquet model approaching the draft like that.
The quality of the audio is very low.
But let me repeat the question because I have his written question here.
All right, good.
I just called him at the last minute. Maybe I should have checked if he could speak. So the question is, the transform matrix is defining a Floquet model in one spatial dimension. It seems to me the transform matrix is defining a Floquet model in one spatial dimension. But you seem to be implying at various points this is a Floquet model in two spatial dimensions. So I think there's a question about how come the transform matrix looks like it's describing a 1D system versus you're talking about Floquet systems in 2D.
Okay, yes, good question. So why transform matrix is one-dimensional? That would be here, right? This transform matrix. Well, but transform matrices are, as far as I know, they're always one dimension below the dimensionality of the whole system. So, for example, in one-dimensional models, transform matrices are even finite size and independent of system size. They just allow you to go from site to site. In two-dimensional models, they do act on a row of spins or sites and allow you to go through this row. In some sense, transform matrix is a map from a statistical mechanical system to a lower dimensional quantum system. Now, it's a little subtle here because my two-dimensional system was already quantum, but still that's the kind of the same idea, the same transform matrix, which is one dimension below. So I would say this is fairly common. And in fact, it's a simplification from the point of view of the numerics. But now I have a transform matrix which is only as big as the linear size of the system, which needs to be diagonalized to find localization length.
So sorry, I was asking why is you have a Floquet model in one dimension that I'm happy with, but you seem to be suggesting there's a Floquet model in two dimensions. That's the part I didn't understand.
Oh, but the Floquet model itself is in two dimensions. So here is the Floquet model. This is a network model. So every link with an arrow has a wave function, has an amplitude. And then I apply an evolution operator which takes this amplitude and moves it along these arrows either to the left or to the right, depending on how scattered is for theta. So clearly that's a two-dimensional construction because I have two-dimensional array of these amplitudes, which are evolving according to this U. Evolution being provided by...
The sharp question, even I'm a little confused now. This transform matrix, what does it mean for the 2D Floquet model? Which object does it correspond to in the 2D Floquet model?
So it studies a particular eigenstate of the 2D Floquet model. Mm-hmm. So suppose I fix my theta and I calculate, so given size here, I calculate size everywhere else. Then what I'm actually doing, I'm calculating an eigenstate of the evolution operator of the next slide with an eigenvalue 1. Mm-hmm. Now you can argue that this is precisely what it means to have network model. So you want to extract from this Floquet evolution an eigenstate with an eigenvalue 1, and that eigenstate is a representative state at that theta for the quantum Hall eigenstate, which we're trying to study. So in fact, that's what I was doing at the very end when I was constructing Chern numbers. I was looking for an eigenstate of this equation with an eigenvalue 1 with an additional twist that I said that theta itself is energy dependent. So if you think about what I'm doing here by applying this technique is I'm constructing a particular eigenstate with an eigenvalue 1. And then I say, oh, that's an eigenstate is a representative eigenstate of my quantum Hall system.
Okay.
And so I'll understand its localization length in this way. And by the way, this slide, which is shown now, it's exactly what I think Chalker and Coddington had in mind when they invented network model. They didn't think of Floquet evolutions. Actually, they did think about it later in 1990s, but in the original paper, they wanted to understand this transform matrix and extract localization lengths from it.
Mm-hmm.
And that's how it was mostly
Let me just quickly go through there are 4 more questions, so let's quickly go through them. So there's a question from Chong Wang. My impression is that U1 symmetry is not very important for the Floquet chiral state, but we know that it is important for the integer quantum Hall effect, in particular for the plateau transition. Could you comment on that?
Okay, the question is how important is U1 symmetry here? It's a good question. So I know that for the integer Hall effect, U1 symmetry is not that important because we can be in class D and we could work with superconductors, which will still have Chern number and still exhibit a Hall effect. Now, I'm not aware that there is an argument that these will have transitions in a different universality class from quantum Hall systems. Actually, I don't think they would, but please correct me if you know otherwise. So then my answer would be that U1 symmetry is just not important for what I'm studying.
So if you're talking about the universality class of a disordered system, then in
Yes.
different AZ classes, of course, they have different properties. Absolutely.
So I would need to I would need to add U1 in class D to have the same critical exponent, for example, right?
Yeah, absolutely. Yeah. Mm-hmm.
I suspect it's you've made that assumption in your scattering matrices somewhere. The fact that you're eventually talking about a U1 conserving system is somehow implicit in the choice of scattering matrices, and different universality, different symmetry classes would have different constraints.
Right. The scattering matrices are restricted according to the symmetries, of course.
Right.
Yeah.
Mm-hmm.
But if you can relax U1 symmetry on the Floquet side, then the question would come up: why can't you relax it on the integer Hall side? If well, okay, it's possible the Chalker-Coddington network model requires U1 symmetry. You just can't relax it.
I think you could relax it and go to some like Nambu spinner formalism and have some particle hole symmetry explicitly enforced, and it would all work the same way. Yeah, as Ilya pointed out, you would get different critical exponents potentially, but yeah, but I think Chong had in mind maybe in the interacting case, the non-number conserving examples give you a lot, give you kind of a much richer class, but those actually require interactions, which we don't know how to incorporate into a network model picture.
I think the question was about the integer quantum Hall effect, so maybe it is about the non-interacting problem.
Yes.
There are 3 more questions. Oh, sorry, did you want to say something, Victor?
Well, okay. Well, I think we should move on, right?
I think the 3 other questions are sort of related to ones that went before, but one of them, let me read out. One is, can the Chalker-Coddington network model hold fracton excitations?
Okay, that's a good question. I don't know the answer to it because I've never seen anything even remotely related to this. But okay, my first reaction would be that fractal excitations are examples of topological order, while here I'm studying a system without topological order. So I guess the question would be if it's possible to devise generalizations of this model for interacting systems, or maybe driven systems, maybe similar to what Ashwin you studied in that model which I showed at the very end, which would actually have fractonic excitations. And whether being driven or being stroboscopically driven allows for new physics. Okay, but I would imagine that's an open question.
Yeah, certainly it would be an interacting generalization. So maybe that's a good point to stop this. Maybe you could answer the other questions on the chat or directly chat with them. But thank you everyone, all the speakers for a very interesting session, and everyone else for coming and participating and asking questions. And we'll see you tomorrow at 12 noon, again, Pacific time, 3 o'clock Eastern time. Thanks everyone.